Let's talk about the ideal gas law. So this is the ideal gas law, PV equals nRT, where P is going to be pressure in atmospheres, V is the volume of a gas in liters, N is how many moles of a gas you have. And a mole is just a counting number. It's a way to say how many gas particles there are, because we know the number of particles affects the pressure. T is the temperature in Kelvin, and R is our gas constant, and it's a constant meaning it's never going to change. So our gas constant is always 0.0821 and has a really long unit, liters times atmospheres per mole Kelvin. If you ever forget what units you're supposed to use for PV, N, or T, you can see them right here in the gas constant. Okay, so these are all factors that affect gas. We've talked about how pressure and volume are related, how temperature relates to gas, and we've talked about how the number of particles has to be constant. So this gas law is going to relate all four of those factors in one equation. So the difference between the ideal gas law and the combined gas law, first of all, there's that N. Second of all of the gas laws we've seen up until this point, we're talking about gases that were changing. So you had a sample of gas that was heated up, or a sample of gas that was placed under pressure. Something about the gas was changed. In this one, you're told all the information about a gas except for maybe one thing, and if you know the other parts, you can figure out that one thing. This can be helpful because if you know that a gas can only reach a certain pressure before it explodes something, then you can figure out what temperature something could rise to before that explosion would happen. Okay, so here are the things we have to be able to do to solve with the PERV-NERT or ideal gas law. First thing is you have to do some algebra. So we'll practice with one. If I know that I have to solve for volume, then I'll start with my equation, PV equals nRT. And I know the thing that I'm solving for is what I have to get alone. So let's get volume alone. It's being multiplied by P, so I'm going to divide both sides by P. And now volume's by itself. So volume is equal to nRT over P. Yay, one done. Number two, the second thing you have to be able to do is convert to the right units, since we just talked about your volume has to be in liters, your pressure has to be in atmosphere, your number of particles has to be in moles, and your temperature has to be in Kelvin. So we'll do this one, we'll do the pressure. So whenever you're converting units, you're going to start with whatever's given. We're given 0.55 atm atmospheres. And you do your little times, fraction bar. Oops. The unit you have goes on the bottom, atm. The unit you want goes on top, kPa. And then you have to find a way that they're related, because you can only multiply it by 1. So the top part has to be equal to the bottom part. And it says 1 atmosphere is equal to 101.3 kPa. Okay, so these are equal to each other. All right, so then I would go 0.55 times 101.3 divided by 1, but you would never type in divided by 1. And the answer I got from that was 55.715. We're going to round that. We're going to round it because this number right here only has 2 measured digits. They're called 2 significant figures. So we're going to round that to this guy right here. Since this is bigger than 5, that 5 is going to go up. So we got 56, and my unit is kPa, kilopascals. Okay, 2 done. Number 3, this one's tricky. All the others are straightforward conversions, which you can rock, but this one is a little tricky. So I'm starting with 10 centimeters cubed, and I know the unit I have has to go on the bottom. The unit I want goes on top. I want inches cubed. And then here's the mistake that I see a lot of students making. You would Google, how many centimeters in an inch cubed, and you would see, or I would just give it to you. There's 2.54 centimeters equal to every 1 inch, and that's exact. Okay, so then I would say 1 by inch, 2.54 by the centimeter. But the problem here is that this is not a cubed relationship, and this is. So if I have centimeters cubed, then I'm multiplying centimeters by centimeters by centimeters 3 times. So I have to divide by it 3 times. So you could cube this whole thing, and that's what I did. So I took 2.54 times 2.54 times 2.54, and I got 16 something. You can type that in. You can do that. So it was 16 something. And then, of course, 1 times 1 times 1 is 1. Alright. So then, when you plug in 10 times 1, but we wouldn't plug that in, divided by 16, whatever that is, you would get 0.61. This is a weird question because I wrote it with only 1 sig fig. So that's 1 measured number. So I'm going to round this to 1 measured number. 0.6 and my unit is inches cubed. Okay. Now let's go ahead and use the ideal gas law. So if I have number 4, question is solve for P if V is 2.5 liters, N is 2.5 moles, and T is 250 Kelvin. We would never talk like that. This question is just a way to get used to using the ideal gas law. This would typically be written as, what is the pressure of a gas when volume is 2.5 liters, there are 2.5 moles of gas present at 250 Kelvin. It's also weird that it's all 2's and 5's. But okay, so obviously, if I'm asking for P, I have V, I have N, I have T, and we always know our gas constant is constant, 0.0821, oops, liters times atmospheres over moles Kelvin. Okay, then we're going to be using this equation. We're going to use an equation that has those variables in it. So PV equals nRT. The next thing I do is, since I'm solving for P, I'm going to have to get P by itself. So I'll undo what's being done to P. Okay, so P is equal to nRT over V. Now we can just plug in. So the N, that was 2.5 moles. The R is the gas constant. Oops, H21 liters times atmospheres per mole Kelvin. The temperature is 250 Kelvin. And the volume was 2.5 liters. Okay, so now we can go ahead and say, you know what, 2.5 divided by 2.5, that's gone. Moles divided by moles is gone. Liters divided by liters is gone. Kelvin times 1 over Kelvin. Kelvin's gone. So we're left with atmospheres. That's a really good unit for P. And we have to just multiply the gas constant times 250. And when you do that, I got 20.525. And since this has 2 digits, and this has 2 digits, and this has 2 measured digits, that 0 is a placeholder, I'm going to round this to 2 digits. Any one of those would have determined that I'm going to measure, or I'm going to answer 2 digits. So 21. And my unit again was, oops, hey, 21 ATM. I don't know why that disappeared. This is a new tool. This ability to write. Okay, and the very last one. Do one that's a little bit trickier because this one, we won't be given the units that we need. So here we have a 3.5 mole sample of gas. It's moles. Do you know what variable that is? Did you say N? Would be right. At 105 kPa. kPa, do you know what variable that is? It's a pressure. Has a temperature of 25 Celsius. I'm not even going to ask you. and we're looking for volume. So we are looking for, oops, I have to move this. We're looking for V. Okay, so before I can plug any of these in, I'm going to have to do some conversions. This is good because N can be in moles. This is not good. Pressure has to be in atmospheres. So I have 105 kPa, and I know for every 1 atmosphere there are 101.325. Can't remember if I used that whole thing in the beginning. kPa. And so that gives me 1.037. Ooh, I totally messed that up. Do you see how? Because kPa is here, kPa has to be there. Oh, how embarrassing. Let's fix that. Okay. I'm working so hard at writing. I'm not paying attention to my maths. Okay, kPa goes down here. Thing I want, ATM, goes up here. 1 atmosphere is 101.325. Okay, and when you plug that in, you're going to get 1.037 kPa. Okay, for the temperature, we know we have to put in Kelvin, and Kelvin is equal to your Celsius temperature, 25 in this case, plus 273. Okay, so that's 298. All right, ooh, Kelvin. So next, set up our equation. PV equals nRT. We're solving for volume, so let's get volume by itself by undoing whatever is being done to it. It's being multiplied by P, so we'll divide by P. So volume is equal to nRT over P. N was 3.5 moles. R is 0.0821 liters, atmospheres over mole Kelvin. The temperature is 298 Kelvin, and the pressure was 1.0. Oops, this was not kPa. All kinds of mess. ATM, right? Because whatever unit you get here, that's your unit. Okay, so that was 1.037 ATM. All right. So if I hadn't caught that mistake, I would have caught it right here because we have to cancel out any units. So ATM divided by ATM is 1, so that's gone. Kelvin divided by Kelvin, that's 1 as well. Moles times 1 over mole, that's gone. So we're left with liters. We're solving for volume, so that's a good unit to get for volume. So then you'll type in 3.5 times 0.0821 times 298 divided by 1.037, and you should get 82.58. Again, let's see, this has 3 measured places. This has 2. This one actually has 3. We're going to go to 2. So 83, since 2 is the smallest. We're limited to 2. Okay, whoops, 83. 83 liters is what you get. Okay, so in general, if you have a question, a problem that's talking about the moles, the pressure, the temperature, the volume of a gas, you'll be given 3 of those 4 things. You also know R. It's really important that all the units match up the units of your R. And whatever you're asked for, that's the thing you're going to solve for. Show your work and make sure you write units, and you're less likely to make a mistake. And if you do make a mistake, like I did, you will catch it when you get to the next step, and those units need to line up. All right, see you in class.